So, okay, today what we will do actually, maybe I'll take a little shorter class. Maybe 40-45 minutes class I'll take today. Okay. Today what we'll do is we'll discuss about incremental algorithm. See, all of us know about this incremental algorithm, the strategy. So we'll take the points, okay, one after other. Suppose if you have a points P1, P2, Pn is given to us. So at the beginning, we'll take the first 3 points, P1, P2, P3, and it forms a sum triangle. And we'll take the next point. Okay, so that point can be inside this triangle or outside the triangle, 2 possibilities. If it is inside, we do nothing. If it is outside, then we will find a tangents and we update this like this. So in general, after computing the convex cell of the first I points, so we have something like this. So I assume that this is the convex cell of I points and I'm denoting by CHI. Now you are taking the I plus 1 point. So this point may be either inside. In this case, we do nothing. If it is outside, it can be anywhere. Then what we have to do is we have to find a tangent from this point to this convex cell and update the convex cell by removing this part. So this is the algorithm, incremental algorithm. So this is clear, no? So now question is how we can check this next point inside this current convex cell or not. That is the first step we have to do it to incrementally construct the convex cell of first I plus 1 points. So given a convex polygon in 2-dimensional plane and a point pi or pi plus 1, how we can check this pi plus 1 is inside or outside? How quickly can do it? Think about it.
So for every line in the convex cell, we can check that whether the point is lying on the same side. If the point is lying on the same side of every line and that is forming the convex cell, then we can say that that point is lying outside the convex cell. And if for some lines it is lying on the right hand side, toward the origin, and for some lines it is away from the origin, we can say it is inside the convex cell.
Yeah. So yeah, your approach is correct. So here we are assume that this convex cell is given to us in counterclockwise direction. Okay. If this point is inside, so if you order these things, okay. So this is what we have. So with respect to each and every edge, of course, we are taking this direction. So this point is on the left side. Similarly, for the next one, it is also left side. So for each and every edge, if you take this direction, okay, this point is always on the left side. Okay, so suppose if the point is outside, for some it is on the left side, for this it is on the left side, okay, and for this it is on the right side. So if your point is outside, for some edges or some supporting lines it is on the left side, and for some it is right side. So in that case, actually we say that this is outside. If with respect to all the edges it is inside, then we call it as a, this is the inside. Okay, is that clear?
Yes, sir.
So how much time this takes?
Order n.
Yeah, linear time. Linear in terms of number of vertices on the convex hull, size of this convex hull. Okay. Now, if we're inside, we do nothing. If it is outside, okay, then what we have to do? We have to find a tangents. So now this is the convex hull given to us, and we know this point is outside, can be anywhere. Okay. So how we can find this? Both the tangents. So if you modify this finding upper bridge of a divide and conquer strategy, we can find out these two tangents. Okay, it's not very difficult. So this can be done again in linear time proportional to the size of this convex hull. Yes. So just work out this thing, how it can be found, how we can find these two tangents. Okay.
Sir, like
So time complex.
we can start from the closest point and move leftward so that all the points are
Yeah.
on same side.
Yes. We can do it. Okay. Maybe you can, the closest point you can start here and start moving this side to find one tangent and move this side to find another tangent. Okay. So this again linear time, finding the closest point and moving. So here time complex is incremental algorithm. Sorry, order n here. So overall time complex becomes n square. So this is not a good idea. So we are not getting a n log n algorithm here. We are getting a higher time complexity. So is this algorithm is everyone? Questions? Very simple strategy. Okay. Now, see here in this algorithm, we are taking the points as they are given to us. Suppose if you sort these points based on their x coordinates as a first step, and then apply this incremental algorithm, what will happen? So we are sorting these points by the x coordinates. So assume that this is sorted sequence, and we are applying the same algorithm. So sorting takes n log n time. Now, if you apply this incremental algorithm, then what happens? So first step, at any intermediate stage, you have a convex cell of first I points. Okay, this CHI. So obviously this is the ith point. Okay, so where will be the I plus 1 point lies? If you draw a vertical line here passing through this pi, okay, I plus 1 point is on the right side of this vertical line. Certainly, this point is always outside this convex cell. So here we no need to check whether this is inside or not. Okay. Now, if it is outside, now we have to find it tangents. How much time it takes? It takes a linear time only. Okay, if you start from here and keep moving to find this tangent and move this side to find this tangent. Okay, so time required to find that both the tangents is time proportional to this length of this chain. Okay, so in worst case it can be a linear, maybe entire convex polygon, maybe there are most part of it may be there, so it linear looks like that. Okay, so again time complexity becomes okay, the recurrence relation becomes same thing, and we're getting a complexity of n square again. Yes, so there is no any change in the algorithm. Only thing is what we're doing, we are sorting these points before by their x coordinates and applying the incremental algorithm. In the first case, the point lies inside the current convex polygon or not, that step is gone, because this next point is always on the right side of this current convex polygon, so it is always outside. Now we have to find out these two tangents. It is the same procedure, there's no any change. Okay, and again we are getting the complex order n square. We are not getting any improvement. Anybody can see some improvement in this time complexity? Algorithm is same, but if you do careful analysis, okay, and you will get a linear time algorithm plus initial sorting algorithm n plus n log n. So after sorting, okay, time complex becomes order n, and sorting everything together order n log n. Okay, I can use this theta notation. Okay, so can anybody see that you can do it in linear time, finding the entire convex polygon in linear time after you sorted these points by their x coordinate? See, we are not modifying any algorithm. Algorithm is same, remains the increment algorithm. Complexity analysis is changed. By doing this carefully, you will get an order and time.
So to find the upper tangent and lower tangent, we are actually eliminating points which are not part of convex cell, and that is bounded by order of n. So the total time to find all the upper tangents and lower tangent is also bounded by order of n for every step.
Yeah, this is a good okay observation. Okay, suppose you have a convex polygon here. Assume that this is CHI first convex cell of first I points. So now you have this I plus 1 point, and you are finding this tangent, and you are finding this tangent here, and you are removing this part. So here there can be any number of vertices on this chain. Okay, so once you remove these vertices, so those vertices can't be part of the future convex polygons. Okay, that means CHI plus 1 or CHI plus 2, okay, and so on. So these vertices can't be part of it. They don't appear again in the future. Okay. Now, number of points we are deleted here. Okay. Let's assume we denote this by say some mi. Okay. Number of points we are removing from this chain here, say assume mi. Okay. So first you have the convex cell of first 3 points. Then you are getting the CH4 convex cell of 4 points. Okay. And convex cell of 5 points and so on up to convex cell of n points. So here you are removing say m3 points, and here you are removing m4 points and so on. Okay. Here you are removing the mn points. And if you add all of them here, okay, that is sigma of say I is equal to 3 to n, and this is how many points we can remove in the entire process. So this is only order n, can't be more than this. So finding all the tangents from the CH3 to CHN is only in order n time. Okay, so once we have sorted these points, then we can find out the convex hull in order n time. Is this clear to everyone?
Yes, sir.
Any questions? Of course, here initial sorting is dominating one, so overall time complexity again n log n. So there is no any improvement. Okay, the gram scan, divide and conquer, incremental algorithm, all are taking the n log n time. So is it possible to find a better algorithm than this one? I mean, better in the sense complex device better than n log n time? If not, we have to prove that this problem has a lower bound of n log n. Okay. So how many of you know that lower bound for sorting is n log n?
So yeah, all of the comparison-based sorting algorithm has lower bound of L log n.
Yeah, all of you remember that lower bound proof, no?
Yeah.
So in that proof, actually, we are proving the lower bound using the basic from this scratch. Okay, so we can use the similar ideas or something, not similar idea, I mean, in the sense that actually you can prove this lower bound for the convex cell also, okay, from the scratch without any other proofs, or we can use the existing lower bounds for whatever the problems we know the lower bound, use those lower bounds and prove that lower bound for this problem also n log n. So we are reducing this lower bound of some algorithm to this one. So here what we do actually, we use the lower bound for sorting. Okay, how we use? Let's see. So suppose for us actually, Now, this is a one-dimensional line, okay, x-axis, and some points are given to us on this one, or you can treat them as numbers, okay. Suppose these are the numbers given to us, we need to sort them, okay. So, okay, some values are given to us, okay, and we need to sort them actually. Normal sorting algorithm, normal sort, okay, we have to put them in left to right order, okay. Yeah, I'm actually mixing the terms here, okay. So here we have a n numbers are given, so we have to sort them in non-decreasing order, okay. So these n numbers can be viewed as a points, one-dimensional points on an x-axis, okay. Just here I'm showing these points here. Of course, these points are given in an arbitrary order. This on the axis they are in an arbitrary order. It's not any particular order, but our aim is to find the left to right order, okay. Now, so what we will do actually, we this is our problem, sorting. What we do, we take a one parabola. So this parabola is equal to equation is y is equal to x square. So you lift each point vertically onto this parabola. Okay. Now you consider the points on the parabola. So basically we have one-dimensional points. Okay. This is mapped to a point in two dimension by this way. Y coordinate becomes square of the x coordinate. So we have a point in two-dimensional plane. Now you find the convex hull of these two-dimensional points. Okay. So what we will get? So this is the convex hull of this. These are the endpoints. So assume that actually this convex hull points on the convex hull given in a counterclockwise direction. Okay. So now you find out the leftmost point here on the boundary of the convex hull and just output the x coordinate of these points one after other in the counterclockwise direction till the rightmost point. Okay. So this is the first one. Okay. And this is the second. Only x coordinate we are outputting from the vertex of the convex hull. And this is the sorted sequence of original problem. We started with a n numbers. Okay. Okay. Of course, these are not in sorted order. Then what we are doing, we are applying this transformation to get a two-dimensional points. Okay. And we are computing the convex hull of the two-dimensional points. Then you find the leftmost point. And then you output x coordinates of points, okay, from leftmost to rightmost. And this is the sorted sequence what you got it. So Basically, we use this convex cell algorithm to find the sorted sequence of initial input. Now you look at this time complexity here. Okay, this is the linear time, and this is linear time, and the final step also takes a linear time. Okay, plus time complexity required for the computing the convex cell. Now, suppose if we have a convex cell algorithm which takes the lower than n log n time complexity, lower order than n log n. I'm using the small o. So lower order than n log n algorithm for a convex cell. Then what happened? You got a sorted sequence lower order than n log n. Okay, it's a lower order than n log n. So which violates the lower bound proof of this sorting. That means we cannot have a convex cell algorithm whose complexity is lower order than n log n. So this is the proof for the lower bound of a convex cell problem. So this is another way of proving the lower bounds for the new problems from the lower bounds of the existing problems. So is it clear to everyone? Any questions? So once again, just I'm repeating what we have actually. We have a endpoints are given to us, not endpoints, n values are given. Okay, so we are interpreting these values as a points on a one-dimensional plane. Okay, and we are vertically lifting these points onto a parabola y is equal to x square. In other words, we are mapping each one-dimensional point into a two-dimensional point like this. So then we are finding the convex cell of these points. Then find the leftmost point. Of course, we are assuming that this convex cell output is given to us as a counterclockwise sequence. So you start from the leftmost point. So find out leftmost point, and from that you start traversing up to the rightmost point or last point. And while traversing, you report the x-coordinate of these points. And whatever the output, this is nothing but a sorted sequence of initial original points. So if you look at this one, so all these steps takes a linear time except convex cell computation. If the convex cell computation can be done lower order than n log n time, so overall sorting algorithm complexity becomes a lower order than n log n, which violates the lower bound proof of this sorting. That means, which is contradiction actually. So only possibility is we cannot have a convex cell algorithm whose complexity is lower order than n log n time. Okay, so basically some sort of proof by contradiction sort of thing. So any sorting algorithm, any convex algorithm must be at least n log n time complex. So this is the proof for the lower bound of this one. So any questions? Okay. The small announcement, I'm using the Teams only for the sake of taking classes. I won't be on the team for all the time. Okay. If you want to send any message, any query, actually, either you raise this in the class or you send a mail to me. Okay. And yeah, this is what I want to make announcement. Don't expect me that I'll be always on the Teams so that I checking your message and replying. Okay. Suddenly I'll check the email and I'll respond if there is you have valid queries are there. So now come back to this convex cell. So we cannot have anything better than n log n time complexity. But if you look at this gift wrapping complexity, so gift wrapping can be done in n log h time. So in worst case, h can be n also. In that case, it becomes a order n square. If h is a constant, it becomes a linear. Okay. Similar way, there is a one algorithm what is called a ultimate convex cell algorithm, which takes a time complexity n log h. Here h is the size of the output. Okay, and there are two algorithms with the same complexity. I think one is in the 80s, maybe. I'm not very sure. I had to check that one. By the two others, Kirkpatrick, Seidel, and title of the paper is Ultimate Convex Cell Algorithm. Okay, you can search on the Google. You will easily find the paper. So in that paper, see, if you want to do something in n log h time, one thing is we cannot do the sorting. Sorting is ruled out. Without sorting, where to do it? Okay, and in this algorithm, authors used very cleverly, okay, order statistics algorithm. Okay, finding the kth smallest element. Okay, kth smallest algorithm takes how much time? Linear time. Do you remember? All of you remember this algorithm?
Yes, sir.
So what I'm advising is all of you go back. Yeah, anyway, you're at home, not going back actually. Just open the algorithms book and go through this, finding the smallest element, kth smallest element, okay, in linear time. So this algorithm is takes a order n time, okay, what is called a prune and search method, okay. So just refresh this algorithm and come back. We'll discuss this, okay, n log h algorithm. So in this algorithm, author used this kth smallest element. Basically, k is take n by 2. It gives a median. Okay. So this algorithm uses repeatedly the finding the median algorithm to get this time complexity. Okay. So in the prudent search, what is the kth smallest element? If you have any algorithm, n inputs, and if you can able to prune a fraction of inputs, say 1/10 of the input is removed, okay, that means you have a 9 and by 10 points left. Points are data elements, whatever maybe. So if this pruning can be done in linear time, so we have a set space of n points, and you spend linear time and remove 1/10 of the input size. Any fraction, 1/10 or 1/4, 1/5, 1/20th, some fraction of you remove it and get the remaining part and use this repeatedly, same thing. So if you solve this one, you will get a order n time complexity. Repeatedly till you get some constant set space. Once you have constant set space, you find out your answer in constant time. So this algorithm takes a linear time. So this is the idea of the prudent search. So this algorithm, what is used in the kth smallest element. So if you remember that it makes a group of 5 elements, 5, 5, okay, and you take the middle elements, and the middle element what you compute, and either you remove this portion or this portion. One fraction is removed, which is not part of the final solution. So this is the technique used essentially in this algorithm to find out this thing. So this algorithm I'll discuss tomorrow. Okay, and there is another algorithm what is called a output sensitive algorithm by Timothy Chan. So that algorithm also takes order n log h, but this is very simple algorithm. Okay, and this algorithm can also be extendable to 3D also. And in this Kirkpatrick, this ultimate convex algorithm, even though you are getting n log h time complexity and finding the kth smallest element, okay, is order n, but this in the kth smallest element, finding the kth smallest element linear time, the constant involved is actually very high. Even though if you are having a recurrence like this, here in this case, the constant involved will be the high, very large here. Okay, so ultimate convex algorithm, even though this complexity wise is n log h, but constant involved will be high. Practically, it's not a very good algorithm for implementation point of view. It is a very difficult and complex algorithm. Okay, and constant involved is high. So then actually Chan came up with a very nice simple algorithm, and basically uses a divide and conquer and gift wrapping. And together it comes this algorithm. Of course, there is one or two other algorithm finding a tangent in logarithmic time it uses. Okay, so using this actually it becomes a very simple algorithm. That also we'll discuss tomorrow. Okay, so with that actually we'll wind up the convex cell. So I'll stop it here and we'll continue tomorrow 12 o'clock. So any questions till now? Okay, so if there's no more questions, I'll stop it here. So we'll continue tomorrow.